Welcome back, ladies and gentlemen. In this video, we are going to start discussing what we know as the triangle mid-segment theorem. The goal of this entire section is to identify and use the triangle mid-segment theorem in the coordinate plane and to find distances of lengths and different segments of a triangle. Specifically in this video, we're going to define what a mid-segment is, and we're going to use mid-segment and its specific theorem inside of a coordinate plane. So let's dive right on in. What is a mid-segment? A mid-segment is just simply a segment that connects two midpoints of a triangle. So M, P, and N are all considered midpoints. How do I know that? Simply because M is the point that is obviously is cutting AB in half, right? These two congruency tick marks show that M is the midpoint. N is the midpoint by these congruency tick marks, and P is the midpoint because of these. Every triangle, of course, then has three of our mid-segments due to the fact that, of course, there are three midpoints, all right? It actually, when these three mid-segments are all in play, we create what we call the mid-segment triangle. And we'll discuss a little bit more about that mid-segment triangle in a couple later videos. What about the theorem? The theorem that goes along with the mid-segment is that it gives us two characteristics, all right? The first characteristic of a mid-segment is that it is 1/2 of the length of its opposite side. So in this case, DE is equal to 1/2 of its opposite side, AC. DE is 1/2 of AC. So for example, if AC was 10, I can tell you that DE, will be 5. I also know that DE is parallel to AC based on it being a mid-segment as well too. And this is really important because we're going to start using triangle similarities, and this mid-segment theory is going to come into play a lot because that means that angle E and angle C are going to be congruent because those would be corresponding angles. Likewise, so would D and A right in here, this angle BDE and angle A, they would also be congruent to one another because they would be corresponding angles as well. So that's important to know as we continue to go on. Let's look at an example here of how we can utilize the triangle mid-segment theorem in some application. So it says, show that the mid-segment MN is parallel, and in fact, that it is half of JL. So how would we show parallelism? Well, keep in mind, this question shows us a diagram on a coordinate plane. So what shows parallelism on a coordinate plane? Hopefully we realize that parallelism and perpendicularism is shown by the slopes of the line. So in order for this to be parallel, MN parallel to JL if and only if they have equal slopes. So let's see if these slopes are the same. So the slope of MN is equal to the change in y. So we're right here at a +2 minus a +3 over the change in x, which is 0, minus a -4. So it's really +4. So we're at a -1/4. Then the question is, do we have the same slope of JL? So the slope of JL, well, we end up having here a -1 minus a +1. And then the x coordinate, the change in x, would be 2 minus a -6. So 2 plus 6 looks a lot like a -2/8, which simplifies to a -1/4. So yes, it is parallel, and we showed it by showing they had the same slopes. The other thing that it asked us for is that can we show that MN is exactly half of JL? Well, think about what this application means. How do we show lengths that are half or equal to each other, or whatever the case is on a coordinate plane? Well, that comes down to our distance formula. So let's find the distance of MN. The distance of MN is equal to the square root of x2, which is going to be 0, minus x1, which is a positive 4, or negative 4, but it becomes positive, plus y2, which is 2, minus y1, which is 3 squared. So we get the square root of 0 plus 4 is 4. 4 squared is 16, plus 2 minus 3 is a negative 1, times itself is a positive 1. And I'm just going to leave it as square root of 17, because that's going to be able to get me to compare whether it is or not. All right. So now what about JL, the distance from J to L? Distance from J to L, once again, is x2 minus x1. Well, in this case, it's a positive, so it'll be squared, plus y2, which is a negative 1. And then we have y1, which is a positive 1, all being squared. So we end up getting 2 plus 6 is 8. 8 squared is 64. Negative 1 minus 1 is a negative 2. Negative 2 squared is a positive 4. So you get the square root of 68. So now we have to actually take into account, is this in fact going to be half of our distance? Well, just looking at it, I guess we might not necessarily be able to just easily say, yes, square root of 17 is half the square root of 68, or whatever the case may be, right? But we can actually simplify this down a little bit and make our lives a little bit easier to identify if, in fact, they are half of one another. Well, 68 ends up really just being 4 times 17, right? So that's the square root of 4 times 17. And 4 is a perfect square. So if I take the square root of 4, I get 2 square root 17. We'll take a look here. Square root of 17 and then 2 times the square root of 17. That ends up being double. So yes, we did show that it is parallel, and we did show it is half of JL.